So we've talked a bit about different estimators that we can use for these different populations. So we talked about finding a sample mean, finding the sample proportion, and things of that nature. What we're going to do is kind of dive a little bit deeper into each of those, but we're going to start with estimating a population proportion. So just to refresh on some of our notation, X is going to be the number of successes. So again, if this is a survey, it's the number of people that agree with that statement. N is the sample size that you pick from. So say you have a full population of individuals, looking at US citizens, that would be whatever number the current population is, but your sample size may only be like 5,000 of those individuals. So capital N is going to represent the true population size. So our sample proportion is found by taking that number of successes and dividing by how big your sample was. So the number of people that responded yes to that survey question over how many there were in the survey. Where the true thing that we're trying to estimate is the population proportion. So this would be the number of successes out of the entire country over the entire amount of the country. So this is the one that's a lot harder to collect because it's very difficult to be able to ask every single individual in that population a question. So we're going to talk about different types of estimates, but the first is exactly what the sample proportion is. A point estimate is a single value used to estimate a population parameter. So here we use a single value. We're not going ahead and collecting a bunch of different ones and then finding the mean of that. This is a single value. So our sample proportion is a point estimate of P, which is the true population. And we know that this is an unbiased and it's our best estimate for the population proportion. So to do a quick example, a survey of 950 undergrad college students showed that 504 took online courses. We want to find the best point estimate of the proportion of undergrad students who take online classes. So again, this sample proportion is the best point estimate. So what we do to find this value of our sample proportion is we take the number of successes and divide it by our sample size. So in this case, successes is they take online classes. So it's the number of students that took online courses divided by the full sample size. So in this case, 504 individuals out of 950 took online courses. And if you plug that in your calculator, it's about 0.53. So 53% of people took online courses. Now, obviously, there are more than 950 undergrad college students. Even at our college, there are way more than that. So this is just an estimator, but it is a single value that estimates the proportion of people that take online courses. What we really want to focus on is how confident are we that this is a good estimate? So this is something that's called a confidence interval. A confidence interval, or often called an interval estimate, is a range of values used to estimate the true value of a population parameter. So this 0.53 or 53% is telling us about 53% of students take online courses. But what I really want is, I know there's definitely error associated to this because it is just a sample. So can I come up with a range around that 53% that I'm confident the true value lies in? And so this is often abbreviated by just using a capital C and a capital I for confidence interval. Now there's actually different types of confidence as well, and that's what our confidence level is. So the confidence level is the probability that the confidence interval does contain the population parameter, assuming that your estimation process is repeated a large number of times. So basically, if you were to do more and more samples, you would be pretty certain that the true value is going to lie within this range. So in addition to calling this a confidence level, you can hear this called as the degree of confidence, or the confidence coefficient. So we have a bunch of different confidence levels, but that probability is given by something called 1 minus alpha. Essentially, we're going to see that there are 3 main confidence levels that are used pretty worldwide, but you can find other confidence levels. So we can have 90% confidence levels, 95% confidence levels, and 99%. These are the 3 most common. But you can still have something like an 80% confidence level. It's just not as nice because 90% is a much better number. So basically, you want to guarantee that if you were to continue doing this, you can say with 95% confidence, my true parameter value is within this range. With 90% confidence, my true parameter value is within this range. So if you ever look up any type of studies, especially medical studies, they usually give this confidence level because they can say, okay, yeah, we're certain with 95% confidence that this is going to decrease maybe some type of cancer cells by this amount, okay? But in the case you have a 90% confidence level, this would mean your alpha is equal to 0.10 or 10%. 95%, your alpha is 5%, and 99% gives you an alpha of 1%, okay? And so really there's going to be a similar way we can find all of these. So if we want to find the confidence interval, it's really all going to boil down to z-scores. So to show you what I mean, we have our standard normal distribution. Smack dab in the middle is going to be our z-score of 0. So that's that mean of 0. And remember, we can always transfer to a standard normal distribution. If, say, I want a 95% confidence level, that would mean between these values, hopefully, 95% of your data is going to be here. So 95% falls within these values. Because of symmetry, these 2 sections off to the side are going to be equivalent to each other. And they account for 5% of data in total. So that would mean this side is 2.5%, and this side is 2.5%. And then also based on symmetry, these z values are the same, just one is positive and one is negative. So if I'm finding a 95% confidence level, that means 5% is going to fall on the outside, which means really half of that is going to fall on either side. So we denote this by alpha over 2. So z alpha over 2 is going to correspond to whatever confidence level you're looking at. So if I want to know this particular z-score, that's going to be the separator. If I can find this one, it'll immediately tell me what this is. So if I want a 95% confidence interval, the area to the left of this would be everything except 2.5%. So the area to the left is 97.5%. which is 0.975. So if I go into my z tables and I look for what z value will cut off my data So that 97.5% is to the left. While going through here, I have exactly 97.5. So my third decimal, or my second place after the decimal, is 0.6, and this is 1.96. So the z-score corresponding to a 95% confidence interval is going to be 1.96. Okay. So now that I know that, we really could do the same thing for all of these others. I could go through, if I wanted a 90% confidence interval, that would mean that 5% is here, 5% is here. So I'm gonna look where 95% of data is. And this one you can actually kind of see what that is. 95% falls in between these two values. So it's somewhere in between 1.64 and 1.65. So really we have a table of our most common used critical Z values. So in the case that you have a 90% confidence level, your alpha is 10%. So 5% falls on either side. And again, that would mean you're looking at 0.95. So it's somewhere between 1.64 and 1.65. And if you use a better Z table than this one, it would be 1.645. If you want a 95% confidence level, that means 5% of your data is going to fall on the outside. And we just showed this critical z-score or z-value is 1.96. And if you want a 99% confidence level, this would be 0.01 for alpha. And you could use your z-tables to see that that z-score would be 2.575. So you would have to go 1.96 standard deviations around that mean, okay? But the problem is now, how do I actually find how this translates into what I need to add and subtract to get a confidence interval? And this is something called the margin of error. So the margin of error, which is denoted with an E, is the maximum likely amount of error. So if I want a 95% confidence interval, I need to figure out what is my associated error that I would need to find to add or subtract to my sample proportion to guarantee I have 95% confidence the true proportion is in this values. So as soon as you find this margin of error E, the confidence interval is given by taking your sample proportion and adding the error, and that gives you an upper bound. And then you take the sample proportion and subtract the error to get a lower bound. So you add or subtract the error, and this gives you a range that you think with 95% confidence the true proportion falls in between. So how do we actually find what this error is? And it actually comes from a relatively nice formula. Might not seem it because there's a lot of letters, but I promise it's not too bad. So in order to find that error, what we're going to do is we're going to take that z-score that's important to us, which is z alpha over 2, and we're going to multiply it by something that's estimating our standard deviation. So the way we do that is we take the square root of our sample proportion multiplied by basically the sample of fails, so the sample that doesn't fall into that category, divided by the number of people in the sample. So this is essentially estimating what the standard deviation is for that sample proportion. And then this is that critical value that we found to guarantee that 97.5 or 95% or 99% or 99.5% of data lies to the left. So just to kind of clear cut what each of these are, the z alpha over 2 is our critical value. And again, we're going to be focusing on these critical values up here. P hat is that sample proportion. So it's the number of people out of however many are in the sample that agreed to that question. Remember, Q hat, or Q in general, tends to stand for failures. So either you agree with the question or you don't. So this is going to be everyone else. So the way we can actually find this is you take 1 and subtract that sample proportion. So you can think of this as the number of fails divided by the sample size. So it's the sample of people that don't agree with the question. And then N still represents the same thing. It is that sample size. So the number of people that were surveyed. So we're gonna work with that same example as above, and we're gonna go ahead and we're gonna find confidence intervals for that. So again, we have a survey of 950 undergrad college students and 504 took online courses. Finding the best point estimator is already what we did, but just to show you within here, that sample proportion is our point estimator. So there were 504 out of 950 people that took online courses, which corresponds to about 53%. Okay. So our estimator is that we think 53% of undergraduate students take online classes. But what I want is how confident can I be this is a true value? I know it's likely not, but can I find an interval that I think the true value lies in between? And so we're gonna start by finding the margin of error E that corresponds to a 95% confidence interval. So again, the way we find E is we take that critical Z value, so this is how many standard deviations we need to be around the mean, and we times it by what we estimate the standard deviation to be. And standard deviation always involves a square root. So I take those proportion of people who are taking online courses, multiply by the proportion of people that are not, divided by our sample size. So filling in all the pieces for a 95% confidence interval, going back up to our chart, our critical Z value is 1.96, so we need to be 1.96 standard deviations within the mean. So this gives us 1.96, and then we go ahead and we times that by a square root, okay? So kind of filling off our pieces to the side, our critical Z value is 1.96. Our sample proportion is 53%. So in that numerator here, we can fill in 0.53. Q would be the sample proportion that does not take online classes. So if 53% do, that means 47% do not. So in the top here, we times that by 47%. And then our sample size is going to be 950. So we would divide this by 950. So definitely need a calculator to go through these. You can use just a basic scientific for it. So just to show you, if we go through this, you do want to go through and do the square root stuff first. You have to fill in the stuff in between and then hit the square root button. So I want to do 0.53 times 0.47, and I want to divide that by 950. So this gives me what's inside the radical, and then I go ahead and press the square root button, and that gives me my square root. And then I need to times that by my z-score, which is 1.96. So ultimately, this gives me my margin of error, and I want to go out quite a few decimals to start. It's 0.031738. So again, this gives me that error associated to my value, which is about 3%. So what I need to do to find my 95% confidence interval is I'm estimating that 53% of undergraduate students take online courses. I want to now add or subtract this error. So I think my true population proportion falls in between the values where we take our estimate and we add the error. We take our estimate and we subtract the error. And this gives us our confidence interval. So our true value, we believe, falls within 53% plus this extra 3% and change. And then on a low end, I really want to do exactly the same thing. So I'm going to copy and paste it over here. But instead of adding the error, we subtract it. So if I go ahead and plug that into a calculator, really just those second digits are going to add, and all of this trails at the end. So on a high end, we can be confident that about 56.2% of people take online classes. On a low end, if I go ahead and subtract this, I'm going to trust you can plug this into your calculator. This would give you 0.49822. So if we round to 3 decimals, that would be 0.498. So what we can say from here is we can be 95% confident that the interval of 0.498 to 0.562 contains the true value of that population proportion P. So one of the most common things is that this gets misinterpreted a ton. So this statement is correct. We can be 95% confident that this interval actually contains the true value of the population proportion. So essentially, the way you can also interpret this, or to go a little bit deeper, is that if we were to do a ton of different random samples with 950 people responding to them, and we construct those corresponding confidence intervals, 95% of them would actually contain the population proportion P, okay? So often that 95% is just referring to the success rate of the process. Still not 100% accurate, but we can be 95% accurate with that. You don't want to say that there's a 95% chance the true value of P falls within these two numbers, because P is a true population parameter with a fixed value. It's not a random variable, so there's not a probability associated to that particular number. It's a parameter. And same thing, you don't want to say 95% of sample proportions are going to fall within these values, because this just came from one single sample, okay? It's basically, if we were to repeat this process over and over and over again with sample sizes of 950, 95% of those samples would actually contain the true population proportion P, okay? So that's why we can say we're 95% confident. So from here, we're now going to try to interpret this a little more. Based on these results, can we safely conclude that more than 50% of undergraduate students take online courses? But if this is our confidence interval, you can see on that lower end, we can have less than 50% of individuals taking online courses. So if my lower bound was, say, 0.501, I could definitely safely conclude this. But because my lower bound falls below 50%, I can't conclude this result. So the answer here is no. The lower bound is 0.498. So it's possible the percentage falls below 50. And you can say it's possible the true percentage falls below 50. So again, it just depends on how much confidence you need, but 95% is typically our go-to. If I wanted 99% confidence interval, you're gonna see it would create a much larger range of values to guarantee that you're in between. But now one of the things we're also gonna be concerned with, well, if I need to estimate a parameter, in this case our proportion P, what sample size should we take to be able to have a certain error associated to it? So if I don't want more than a 10% error, how many people should I sample from that true population? Or if I only want a 1% error, what should I pick as my sample size? And really, it just comes from solving our equation for E, okay? So we know that our error is going to be that critical Z value times this square root, where we take P hat, times it by Q hat, and divide it by the sample size. What I want to do is I really just want to solve this for N, because that's the sample size. So in the case, I know I'm looking for 95% confidence. I know estimates for my sample proportion, and I want a specific error of 1%, 2%, 3%. Can I find N? So if I want to get N on its own, the only way I can get rid of a square root is by squaring. So this would go ahead and cancel these two operations out. But if I'm squaring one thing when I have this multiplication, I really need to square everything. So this gives me my error squared is equal to whatever that critical Z value is squared. And then I have my P hat, Q hat over N. And again, I want to solve for N, so I don't like that it's in the denominator. So I'm going to go ahead and multiply this side by N because it will cancel out, which means I need to do the same thing over here. So that gives me my sample size times the error squared is equal to my Z-score squared times my sample proportion times my sample failure, I'll call it. And then to get N on its own, we need to divide by E squared, which means I need to do the same thing on both sides. So if you're ever stuck, as long as you know one formula, you can rearrange it for the other. So the sample size we would need to have is going to be that Z-score squared times P hat times Q hat over the error squared. So this gives us how many people we should survey to be whatever confidence level we want within a certain margin of error. Now, if you don't know these estimates, what we're going to do is just assume that it's 50-50. So in this case, we're going to replace both P hat and Q hat by 50%. So in this way, when you go to take the product of these two, 0.5 times 0.5 gives you 0.25. So all that happens is right up here is replaced by 25%. So the number of individuals you would need to sample is that Z-score over 2 squared times 0.25 over whatever error you want squared, okay? So we're gonna do just one last example where we need to figure out what should I make my sample size be. So a survey of 4,780 randomly selected adults showed that 79% shopped online. If we wanted to conduct a new survey, maybe a couple years later, to determine whether that percentage has changed, how many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? Okay. So in this case, I know my sample proportion, so I want to use this formula instead. So I'm going to start by copying down the formula, and then I'm going to figure out what are each of the values here. So the number of people I need to sample is whatever that critical Z value is squared times P hat times Q hat divided by the error squared. In this case, our alpha is we're dealing with a 95% confidence interval. So alpha's 5. And we know the critical Z score corresponding to that is 1.96. My error in this case is 3 percentage points. I want the error by no more than 3 percentage points. So as a decimal, that's 0.03. And then we do have information already about what that sample proportion was. It was 79% of people that shop online. So as a decimal, that's 0.79, which means our sample failures is 1 minus that, which is 0.21. So 79% of people shop online means 21% of them do not. So the number of people we would need to sample would be that 0.196 squared. P is 0.79 or P hat. Q hat is 0.21. And my error is 3%. So plugging this into the calculator, we need to do 1.96 squared. So I press the square button. We're going to times that by 0.79, times that by 0.21, and that gives us our numerator. And then I want to divide that by 0.03 squared. And so this gives us a decimal, which is 708.13. We obviously cannot have 0.13 of a person. So in this case, you're always going to round it up. You don't want to take less people. You need to take more to get that true confidence interval. So the number of people that we should have in our sample size is going to be at least 709 people. Okay. So if you didn't have this original survey and knowing that it was the 79% result, instead, again, what you would do here is put the 0.5 and 0.5 to make it 0.25. And you would see you probably actually need a lot more people to get that true confidence interval within 3 percentage points.